Hi guys, today we are going to expand on what we learned about sigma notation in 1.7, and we are going to talk about recursive sequences. So let's get started with some definitions. So sequence and series are two words that we're going to learn the definitions of. We've already talked a little bit about the word series, but let's go ahead and give these a formal definition. So a sequence is a string of numbers that follow a particular pattern. Each number within the sequence is called a term. Okay, so we have, for example, 2, 4, 6, 8, 10, 12. Notice my numbers here are just a string of numbers. They're just separated by commas. And notice that there's a pattern to these numbers, right? 2, 4, 6, 8. We're just adding 2 each time to get adding 2 to the previous term to get the next term each time. So that is the sequence, okay? Any string of numbers that has a pattern to it is called a sequence. Okay, a series is the sum of the terms of the sequence. So just like in 1.7 when we added up all of these numbers in a string, that's called a series. So the difference between a sequence and a series is a sequence is just a list of the numbers, whereas a series is the sum of that list of numbers. So, for example, 2 plus 4 plus, right? They're all added together. So, a series can be summed, like we can just write it as one number that after we sum these all together. But we've written it here like this so we can see how they compare to one another, sequence and series. Okay. Alright, so a couple more definitions really quickly. An infinite versus a finite sequence. Okay? A finite sequence has a fixed and countable number of terms, whereas an infinite sequence has an infinite or uncountable number of terms. So, for example, if I have a sequence that looks like this, 1, 2, 3, 4, 5, and it ends at 5, I can definitely count how many terms this has. It has 5 terms. So this is a finite sequence, okay? I could also do like 3, 7, maybe 1. Okay. Another is a sequence because there's a pattern to numbers. We're multiplying by 3 each time to get to the next number. And it's finite because there are 4 terms. I can count how many terms there are. An infinite sequence is going to have an infinite number of terms. So it might look similar to a finite sequence. The difference is that it's going to tell you this pattern keeps going and it doesn't end, right? It's just going to keep going indefinitely. They're just going to be counting forever if you want to find the next few terms. So similarly, I could do 3, 9, 7, 1, ... That tells me it's going to keep going. We're going to keep multiplying each number by 3 to get the next term. We can't count how many terms it has because it's going to go on and on and on. Sometimes we write sequences as strings of numbers. They can also be written as a formula with an index. So we did that a little bit with our sums and our series. But this time we're just going to talk about what kind of formulas might give us a sequence. Alright, so we're going to go ahead and we're going to write out the first few terms of this sequence. This tells me that n is the index. Okay? So the notation here is saying I'm going to be starting at 1, and I'm going to be plugging in 1 to my formula over here. So it'll be 2 times 1 plus 7 will be my first term. Then I'm going to keep going. I'm going to go up to 2, and I'm going to put in 2 here, and I'm going to plug in 3. I'm just going to start at 1 and keep going. So the first term, we call it T1, so this right here means the first term, because I'll get one up there, would be 2 times 1 plus 7, which is equal to 9. So my first term is 9. My second term, I would form 2 right here. This is telling me that that's term 2, would be 2 times 2 plus 7. So that's 4 plus 7, which is 11. Term 3 is going to be 2 times 3 plus 7, so 6 and 7 is 13. There's no stopping point here given, right? It's just telling me to keep going because it doesn't specify an ending value. Okay, so those are the first few terms of our sequence. Oh, I wanted us to write out the first 5, right? So we start at n equals 1, so let's start with 2, 1. 2 times 4 plus 7 is equal to 8 plus 7, which is 15. What pattern are you noticing here in line 9, 11, 13, 15? So I could probably go ahead and write out term 5 without using the formula. I know they're going up by 2 each time. So those are my first 5 terms. Could we continue writing terms? Absolutely. We could write term 6, term 7, we could keep going indefinitely. So because of that, is the sequence finite? No, this would be an infinite sequence because we can continue writing terms indefinitely. It didn't give us any type of stopping value. Alright, so now we're ready to talk about what is a recursive sequence. Okay? A recursive sequence is a sequence in which the first term is given and then used to determine subsequent terms. So it's going to tell you term 1 equals this. Now use this to find term 2. Okay, it's also going to give us a formula so that we can do that. So, for example, if I know that term 1 is equal to 5 and Tn is equal to Tn minus 1 plus 7, then I can use that in order to find the terms of the sequence. Okay, so again, let's write the first 4 terms of the recursive sequence. So let's talk a little bit about the notation here. So this is my index. It's going to start at 1 and it's going to go up from there. 1, 2, 3, 4. This right here tells me in order to find term 2, in this case, I'm going to have to take term 2 minus 1. Okay, so this n and this n should match. So term 2 is equal to term 2 minus 1 plus 7. Okay, so that tells me this is term 1. Whoops. So term 2 is equal to term 1 plus 7. Well, I know that term 1 is 5. So term 1 was given, it's 5. Term 2 I can find by plugging in term 1 to my equation. So 5 plus 7, which is 12. Okay, term 3 is going to be equal to term 3 minus 1 plus 7, which is equal to term 2 plus 7. And I know that term 2 is 12. So 12 plus 7, which is 19. So there's term 3. Term 4 is going to be term 4 minus 1 plus 7. So term 4 is going to equal term 3 plus 7. This is why it's called a recursive sequence, because you always take the previous term and then you plug it into your formula. So this would be 19 plus 7, which equals 26. Those are our first 4 terms. 5, 12, 19, and 26. Alright. An arithmetic sequence is a sequence with a constant difference between terms. So, for example, if I have this sequence 3, 7, 11, 15, and 19, I can see that between each of these terms there is a common difference. Okay, if I take the previous term and subtract, if I take the second term and subtract the first, it gives me 4. So the difference between these 2 terms is 4. If I take the difference between the second 2 terms, 11 minus 7, that's also 4. 15 minus 11 is 4. 19 minus 15 is 4. Because that difference is the same each time, I know this is an arithmetic sequence. That is because of that common difference between terms. So we're going to call our common difference D. So what is our common difference here? It's 4, because each time we went to a new number, 4 was added to it. Okay. So the difference between each of the 2 terms is 4. All right. So a geometric sequence is a sequence with a constant ratio between terms. So a ratio means we're going to be, instead of adding or subtracting here, we're going to be multiplying. So what do I have to multiply by to get 5? Or what do I have to multiply 5 by to get 25? In order to find this, we always take the second term over the first term, the third term over this second term, and these should be the same each time. The fourth term over the third term. Any 2 subsequent terms, we put the second over the first. we should get the same value if it is a geometric sequence. And this one, as we see, is because each of these is equal to 5, which means our common ratio is equal to 5. In order to find the next term, I would just go ahead and multiply 625 times 5, and that would give me my next term. I can grab a calculator here, and 625 times 5 is equal to 3,125. Okay, so that would be our next term. We should go ahead and continue finding terms using our common ratio because we know that this is a geometric sequence because the ratio is the same between each term. All right. Determine if each sequence is arithmetic, geometric, or neither. So we're looking for those common differences or common ratios. If it has neither one of those things, it's going to be neither. All right. So let's go ahead and check here. If I have 1 minus negative 5, I'm taking the second term and subtracting the first. That gives me a 6. That's 1 plus 5, right? If I take 7 minus 1, it also gives me 6. 13 minus 7 is 6, and 19 minus 13 is 6. So we have a common difference. So this would be a geometric sequence. I'm sorry, it would be an arithmetic sequence. And what is D? D is 6. Okay, what would be the next term after 19? We'll just add 6 to 19. It would be 25. Okay. Second example. Check for that common difference. So 10 minus 6 is 4. 14 minus 10 is 4. 18 minus 14 is 4. 22 minus 18. They're all 4. So we do have a common difference again, which means this is arithmetic. It's an arithmetic sequence. Because of that common difference, our common difference is equal to 4. And our next term, just add 4 to 26, would be 30. Okay, and we could keep going and adding 4 and adding 4 and getting more and more terms. 2, 6, 18, 54, 162. We have 6 minus 2 is 4. 18 minus 6 is 12. So obviously it's not arithmetic. Let's check to see if it's geometric. If it's geometric, we would take second term over first term. So 6 over 2 is 3. Then 18 over 6 is also 3. 54 over 18 is 3. And 162 over 54 is also 3. So here we have a common ratio, which means this is geometric. A geometric series. And what is R? We already found R, it's 3. And what would our next term be? Just take the last term and times it by our common ratio. So 162 times 3 will give us our next term, which is 486. And we could keep going, we could find more terms, but it was just asked us to find one, so forward. Alright, so here we have 15, 3, 3/5. It does not look like we have a common difference between terms, so I'm going to check for a common ratio. We're going to take the second term and put it over the first. And 3 over 15 gives me 1/5. I can just simplify that down and get 1/5. My second term would be 3/5 over 3. So if I have a fraction divided by another fraction, I take, well, a whole number, I can take it and turn it into a fraction. And then if I'm dividing a fraction by a fraction, the way I actually do that is I flip the second one or the bottom one over and multiply by the reciprocal. It might have been a while since you've done that, but that is what it gives us. It's 3 over 15, which again simplifies to 1/5. If I took 3 over 25 over 3 over 5, again I take the bottom one and invert it and take the reciprocal and multiply. 3 times 5 is 15, and 25 times 3 is 75, which is also 1/5. So this is a geometric sequence. We could check the other term, but I don't think it's necessary. So it is a geometric sequence, and r is 1/5. Okay, it does have that common ratio of 1/5, which just means each term is being multiplied by 1/5 to get the next one. So in order to find the next term here, I would take 3 over 125, and I would multiply it by my common ratio, which is 1/5, which would give me 3 over, what 125 times 5 is, 625. Alright, so there is my next term. Okay, let's try another one. We've got 1, 4, 9, 16, 25, 36. If I look for a common difference, 4 minus 1 is 3, whereas 9 minus 4 is 5. So already I can see it's not arithmetic. Geometric, I would do 4 over 1, 9 over 4, 16 over 9. These are not equal. So it's not geometric or arithmetic, so this one would be neither. Okay. And then how do you know it's neither is what my question underneath there says. We know it's neither because there's not a common difference, and there's also not a common ratio, so it cannot be either. Alright, what would the next term be? Can we still find the next term here, even though it's not arithmetic or geometric? There's still a pattern, isn't there? So it looks like this is 1 squared, 2 squared, 3 squared, 4 squared, 5 squared, and 6 squared, which would make our next term 7 squared. So even though it's not arithmetic or geometric, it still has a pattern, and we could still find the next term in that case. Alright, let's do some erasing here really quickly so that we can see what we're doing. Okay, so we have 2, -8, 32. This is definitely not an arithmetic sequence because the difference between -8 and 2, -8 minus 2 would be -10, whereas 32 minus 8 would become 32 plus 8, which is 40. There's not a common difference there. Let's see if there's a common ratio. So I take the second term over the first, third term over the second, the fourth term over the third. -8 divided by 2 is -4. 32 over -8 is -4. -128 divided by 32 is -4. So this does have a common ratio, so this is geometric. And my r is equal to -4. What would my next term be? 512 times -4. You can calculate that out with your calculator or in your head, but that would be the next term. Okay. Alright, so now yesterday, or in section 1.7, we evaluated the sum of some series. This one we could definitely do the same method we did last time, but notice that my index goes from 1 to 95. This could take a while, right? That's a lot of terms to write out. So because of that, we will want to use a formula if there's a large span on our index. So if it goes from 1 to 95, I don't know about you, but I don't want to plug in 95 different numbers and evaluate them and then add them all together. So let's look at a formula instead. It does also work if our span is small. So if this only went from 1 to 4 or something, the formula would still work. Okay? So here's our formula. So let's look at the different parts of our formula. So we have S of n. That would be the sum of all terms. So that's basically what we're looking for. We want to sum it up. The n in this formula is the total number of terms. So this n right here. If there's 95 terms in my sequence, then that would be a 95. Okay. The T1 is the first term of the sequence. So that means I plugged in 1. Tn is the last term of the sequence. So I would take the number on top of my sigma and plug it in to get that term. And let's go ahead and try it for the same formula that we had on the previous slide. So S of n is what we're looking for. So let's just say it's all of this. It's going to equal n. Remember, that's the total number of terms. So if I'm going from 1 to 95, that means there's going to be 95 terms, right? So take 95, divide it by 2, and then we're going to multiply that by our first term plus our last term. So our first term would be plug in the first index number. So 2 times 1 minus 3, that would be our first term. So this is T1. So that gives me 2 minus 3, which is negative 1. So I'm going to have a negative 1 here. I'm going to add on the last term. The last term comes from plugging in 95. So this is T to the n, Tn, or T95. It's our last term. So we're going to plug in 95 and subtract 3. So 2 times 95 would be 190 minus 3. So this would be 187. So now go ahead and calculate this. 95 over 2 times 186. And I'm just going to plug that in really quickly to my calculator. So 95 divided by 2 times 186 is 8,835. Oops. 8,835. That's a big number, and that would have been a lot more work to write out each term, right? So I'm glad that we could find a better way to do that. Alright, so let's take a look at our next slide. Alright, so now we're going to do the same sort of thing, but we're going to look at it for a geometric series. So I guess you do need to know whether or not your series is arithmetic or geometric, and you do that by listing out some terms, right? But if it's arithmetic, you're going to use the previous formula. If it's geometric, you're going to use this one. This is to find the sum of the series. If it has all those so many terms that you just can't write them all out and add them all up, these formulas will help you to do it more quickly and concisely. So this one, let's look at the parts of it first, and then we'll do an example. So S of n, again, is the sum of all the terms. So that's what we're looking for when we have a sequence or a series that we have to find the sum of. N is the total number of terms, again. So this right here, where I plug in, and I'm going to have to know how many terms there are, and I look at the index and where it starts and stops to find the number of terms. N is, or sorry, A1 is not just a steak sauce. It is also the first term. So we'll plug in the first term out here. And then R is our common ratio. So we have to find our common ratio also in order to be able to do a geometric series. So let's look at an example here. So first of all, when you have a series, you need to determine, is it arithmetic or is it geometric? So even though there's 50 terms here and we don't want to have to write them all out and add them all up, we can write out the first few just to see what the pattern is, to see, am I dealing here with arithmetic or geometric? So if I plug in 1 to this formula, I'm going to get 3 times 2, which is 6. If I plug in 2, 3 squared is 9 times 2 is 18. If I plug in 3 to the third power is 27, and 27 times 2 is 54. And I'm going to do one more term here. We'll plug in to the fourth. 3 to the fourth power is 81, and 81 times 2 is 162. So I can see it's not arithmetic because there is not a common difference here. But let's check to see if all of these these ratios are the same, and they are. 162 over 54 is 3. So because I wrote out my first few terms and I see they all have a common ratio, I know it is geometric. So I can go ahead and use this formula in order to calculate what this sum would be without writing out all 50 terms, right? So let's go ahead and find our sum. So S of n, that's the sum of everything, that's what we're looking for, equals our first term. We already put our first term here is 6, times 1 minus our common ratio, which is 3, to the power of how many terms are there. And if I start at 1 and go to 50, that means there's going to be 50 terms. If this doesn't start at 1, you do have to be a little bit careful. Like if it started at 0 and went to 50, there would actually be 51 terms instead of 50, right? So you have to just be thinking about that. How many terms are there actually? 1 minus our common ratio on the bottom. And notice here that r cannot be equal to 1. But if r were equal to 1, basically our sequence would just be the same number over and over again, right? 2, 2, 2, 2. Because that would be 2 over 2, 2 over 2. So if our number is the same, repeating over and over again, this is not going to work. It's not going to help us. So just keep that in mind. Okay, so let's go ahead and evaluate this now. So I've got to be careful with my order of operations. Think about the order to do things in. I want to start inside the parentheses on the top and the bottom individually first. If I have 3 to the 50th power and I also have 1 minus in front of it, I definitely want to do this first. I want to do the 3 to the 50th power before I do 1 minus that number. So 3 to the power of 50, I'm going to hurry and plug this into my calculator. It's going to give you a really large number, right? 3 to the 50th power is very large. And then you want to plug this into the formula, 1 minus that number. You can, if you're careful with your parentheses, you can just put this entire formula into your calculator just as you see it, and that will also give you the correct answer. So I've done that here, and I got 2.15, and then there's a bunch of decimal places. I'm not going to write all of them down. I'm going to round one of them off here. But then it says at the end, E24. Okay, this is talking about scientific notation. This means this decimal place belongs 24 places that way. Sometimes you say it, you'll see times 10 to the 24th power. Same thing. This decimal place belongs 24 places that way. So this is an extremely large number, an extremely large sum. And the formula is definitely going to help us out in summing that up so that we don't have to write all those terms out, right? All right, let's take a look at the next slide. Write the formula for the nth term of an arithmetic sequence. So basically, we want to write that formula that t of n equals in the recursive sequence so that we can plug in any term and find out what the next term is. Okay. So I know here that my first term is 6, and I know that the common difference is 5. Okay, so how are we going to do this? How will we come up with a formula? So the first step is we're going to write out the first 4 or 5 terms of the sequence and look for a pattern, right? And we can do that because we know the first term, we know it starts at 6, and we know the common difference is 5. So in order to write that out, we just have to add 5 each time, starting at 6. So 6 plus 5 is 11, 11 plus 5 is 16, 16 plus 5 is 21, and 21 plus 5 is 26. So here's our first 5 terms. What pattern are we looking at? Well, let's write them a little bit differently. So we have our first term is 6. We have our second term is 6 plus that difference, right? 5. Okay, and then our third term would just be, well, take the previous term, right, which is 6 plus 5, and add our difference to it again. Our next term would be take the previous term and add up our difference to it one more time. So what's really going on here? We have 6 as a steady throughout all of these numbers. That's our first term. So let's call that T1. Okay, T1 is 6. That was our first term. We already had that. But just for our formula here. Our difference is 5, and it looks like on the first term, we're adding 5 0 times. On our second term, we're adding 5 1 time. On our third term, we're adding 5 2 times. And then we're adding 5 3 times, and we're going to continue to go up by 1. So we have 0 times, 1 time, 2 times, 3 times. The next term we'll add 5 on 4 times, right? So we're adding on that common difference of D, and we're doing it one less time than it is a term that we're on. So for example, if my term here on this first one is term 1, I'm doing one less than that because I'm adding 5 on 0 times. On the second term, when it's term 2, so this is term 1, term 2. When it's term 2, I'm adding it on 1 time. When it's term 3, I'm adding it on 2 times. So I'm doing it 1 less than the term number, right? So t, the nth term would just be written as 6 plus 5 times n minus 1. Every time we take 1 less than whatever our term is, and we times it by 5, and we add 6 to it, that's going to give us any term of the sequence. Okay? So let's write the formula for the nth term. Well, we already did it. T to the n equals 6, and 6 was our first term, right? Then we're going to add on the common difference. We're going to do it times the number of the term number that we're on minus 1. That's how many times 5 will get added to 6. Okay? So in general, the formula for the nth term of an arithmetic sequence is number 6. That was our first term. So Tn equals T1 plus our 5, which in this case was, well, in this case it was 5, but in general it's our common difference. And then times this by whatever term we're on minus 1. Right? That's going to give us the correct number of times that we're multiplying, or sorry, that we're adding on that common difference. Okay, so this is the general formula. So write this down. Anytime you're working with an arithmetic sequence and you need to find the nth term, you can use this formula. We can go through it logically and write out the pattern and see how many times we're adding on that common difference, but it always works out as 1 term less times that common difference plus the first term. Okay. So I had it written there already. So go ahead and make sure you have that written down. Okay. Now, if we have our sequence as 3, 10, 17, 24, and 31, we're going to do the same thing. We want to write the formula for the nth term. So we can use the formula we wrote down, or we can look for our pattern in the equation, which I'm going to do that one more time just to make sure you understand what's going on. So find D. So it looks like our D is 7 here. These all have a difference of 7 between them. So D is equal to 7. Our first term is 3. So T1 equals 3. Okay. Now 3 is our first term. Our second term is 3 plus 7. Our third term is 3 plus 7 plus 7, right? Every time you're going to add it on another 7 because that's our common difference. If this is our first term, so if this is T1, then I have that first term, and I'm adding on our common difference, which is 7. I'm adding it on 0 times. And the way I get that is by putting that n minus 1 in there. So that's the term number. If it's term 1, that's going to become a 0, and I'm just going to be left with a 3 because 7 times 0 goes away. On the second term, it's the first term plus the common difference times how many times. That's going on there. If it's the second term, I subtract 1 off of that. That gives me that next term 10. Okay, so let's write down our formula here. So we have the nth term is going to be equal to the first term plus the common difference, and then just the term number minus 1. Okay, there's our formula for the nth term of the sequence. So if we are asked to find the 35th term, all we have to do is plug into this formula 35. So just like that. So 3 plus 7 times 34 is going to be the 35th term of this sequence. So 7 times 34 plus 3 is 241. Okay, pretty slick. Alright, so now notice we have switched to geometric sequence. So we're going to write the formula for the nth term of a geometric sequence. And we're going to start by, again, writing out the first terms and seeing what the pattern is. So if my first term is 10, and my common ratio is 2, I know I need to multiply my first term by the common ratio in order to get the second term. So 10 times 2 is 20. Do it again. 20 times 2 is 40. 40 times 2 is 80. And 80 times 2 is 160. So there's my first 5 terms. But again, let's write them out and look for what pattern just happened. On the first one is just 10, right? The second one was 10 times my common ratio, so 10 times 2. The next one is going to be the previous term times 2 again, right? So each time I'm just multiplying 2 on one more time. Okay, so think about how I would write this in an equation. So it looks to me like I start with my first term, which is 10, and then I want to multiply it times 2, and I want it to be multiplied by 2, one less than what my index number, or what term number I'm on. So I've written out 10 times 2 to the n minus 1. Let's see if that is true. So here's term 1. So if n is 1 in this formula, that gives me 10 times 2 to the n, or 1 minus 1, right? Because it's the first term. So 10 times 2 to the 0 power. And remember, anything to the 0 power equals 1. So that's just 10 times 1, or 10. So that gave me my first term. Let's see if it works for my second term. So for second term, I would have 10 times 2 to the 2 minus 1. So this was term 1. No, that was term n. This is term 1. Term 2 is 10 times 2 to the 2 minus 1, or 10 times 2 to the first power, which is just 10 times 2, which gives me the 20. Term 3 would be 10 times 2 to the 3 minus 1, or 10 times 2 squared. So again, that 2 is getting multiplied on 2 times on this one. So this would give me 40. Okay, so it is working out. So in order to get the nth term, I would have t to the n equals 10 times 2 to the n minus 1. In general, the formula, I probably already wrote it down. This right here is the first term, and this right here is r. So just a to the n. Okay, I used a instead of t in this one, but it's the same thing. So the sum of all of the terms, or I'm sorry, the first term, the second term, the third term, the nth term is equal to the first term times the common ratio raised to the power of n minus 1. So in general, if you know your series or your sequence is geometric, you can always use this formula to find the nth term. You just need to know the first term, and we need to know the common ratio, and we don't need to know which term we want to find. Okay? So let's do one more example. My sequence is 100, 50, 25, 12.5. Okay? I can see that this is not arithmetic. It's not giving me, I subtract 50 to get here, I subtract 25 to get here, so that it doesn't have a common difference. If I put 50 over 100, 25 over 50, 12.5 over 25, I see that it does have a common ratio, and that r is equal to 1/2. Okay, so let's go ahead and find r. Well, we just did that. Okay, let's write the formula for the nth term. So we can look for our pattern, or we can use our formula. But again, I start with 100. That's my first term. This is term 1. I guess in this one it's using a, so we'll use a. So a1 is 100. a2 is 100 times our common ratio, which is 1/2. It gives us the 50. a3 is 100 times 1/2, which is 50, and then times 1/2 again. a4 just is the same thing, except we multiply it again by 1/2. So our formula for the nth term is going to be, take your first term, which is 100, times it by your common ratio, which is 1/2, and raise that to the power of n minus 1, right? N minus 1 because we always multiply the next one by 1/2 one more time. We started with timesing this by 1/2 to the 0 power, so it's the first power. So that's why there's an n minus 1. So that is our formula. Now we can use our formula to find any term. Let's find the 15th term. So our 15th term would be 100 times 1/2 to the 15 minus 1 power. I'll quickly put this in my calculator. And it is equal to 0.0061. And I'm going to stop there. It goes on. Which makes sense, right? These numbers, every time they are getting divided in half to get to the next term, it's going to start getting pretty small. Okay. All right, so now one last example before we end. This is one of our longer videos, so we might divide this into 2 days. But now try this. Given that term 2 is equal to 8 and term 6 is equal to 2048, in a geometric sequence, find T5. Okay, so we have a couple of terms here. We don't know what the common ratio is yet, but we need to find one of the terms that's in between these two. There's probably more than one way to do this. This is what makes sense to me, okay? So if I have term 2 is equal to 8, I know that term 3 is going to be 8 times the common ratio. Even though I don't know what the common ratio is yet, I know that's how I'm going to have to find it. I know that term 4 is going to be the same thing times r one more time, right? To get to a next term, you always just multiply it by r again. So the 5th term is going to be 8 times r to the 3rd power. And then I know that the 6th term is equal to 2048, but I also know it equals a times r times r, right? I know that it has r times 4 times to get it, but I also know it equals 2048. Okay, and this I can use. Okay, ar to the 4th equals 2048. I can solve that because there's just one variable in it. So in order to do that, I'm going to divide both sides by 8. I'm doing this so I can find that common ratio, right? So I know that r to the 4th power excuse me, is equal to 2048 divided by 8, which is equal to 256. Whoops, an extra equal sign there. Let's just get rid of that. R to the 4th equals 256. Okay, that's r to the 4th power. I need to know r to the 1st power. In order to undo a 4th power, I can take a 4th root. So I'm going to take a 4th root of both sides of this equation. Well, that will just leave r. And if I take the 4th root of 256, that r equals 4. Okay, so I used what I knew. I know how geometric sequence works. You multiply the previous number by some common ratio every time. I used that and the fact that I know that term 6 is 2048 to solve for and find my common ratio. Now that I know what the ratio is, I can find the 5th term. I know that the 5th term is 8 times r 3 times, right? So 8 times 4 cubed, or 8 times 4 times 4 times 4, same thing. Now in order to evaluate this, do the exponent first, so you're going to do 4 to the 3rd, and times it by 8, and it is 512. Okay, another way to have found it would be 2048 divided by 4, because we know the previous term had 1 less r in it. So that's one way to do it. I know this has been a long video. Hopefully we can divide it over 2 days or something, but I hope you guys have a great day, and we will see you later.